Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to take a look at an advanced topic in computer science, and that is creating user-defined functions, including recursion. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists for tonight, Tony Norell and Michelle Reinhardt. Tony has over 25 years of teaching experience from 5th grade all the way up to college algebra. She works as a math specialist and a TCube regional instructor, and she is the recipient of the Presidential Award for Excellence in Math and Science Teaching. Currently, Tony and Michelle are developing and delivering computer science professional development all over Texas. Tony, so great to have you with us tonight. And born and raised in rural Ontario, Michelle studied mathematics, physics, and education before moving to Texas. Michelle has taught high school math and science at rural districts in Texas, while also working as a math and science consultant throughout the state. Her interests include technology integration, conceptual understanding, and curriculum and instruction. Michelle, thanks so much for being with us tonight.
Thanks, Mike. Glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Michelle or Tony using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'll also provide a link for all the documents that Michelle and Tony will be using tonight. And we found that the best way to really interact tonight is to kind of sit back, watch what they're doing. If there's some questions, maybe think about those questions and respond. But don't necessarily grab your handheld tonight and try and follow along step by step. That's really best done with the recording, which you're automatically going to get in an email in a couple days. With that recording, you can really go at your own pace and pause and rewind as necessary. We hope you don't have any audio issues, but in the event that you do, find a little icon next to your name that looks like a little telephone, and by clicking on that icon, you'll get call-in information, and you'll be able to pick up a phone and actually switch from the audio broadcast over to actually calling in using a phone, which should alleviate any further audio issues. At this point, Tony is going to discuss our agenda.
Thank you, Mike. Can you hear me?
Yep, you sound good.
Okay, great. I think I was having some issues a minute ago. Thank you. Welcome, everybody. Tonight, we're going to talk about advanced topics in computer science, user-defined functions, including recursion. So we're going to start out looking at defining recursion and working a recursion example. And then we have some recursion challenges for everyone to see. And then Michelle's going to look at user-defined programs on Rover, and then user-defined program challenges. And then we'll look at some online resources.
Thanks so much, Tony. And Michelle is going to discuss some expected outcomes for tonight.
Thanks, Mike. So by the end of this session, we will have created some user-defined functions and procedures together. We will have traced through and used a number of recursive algorithms, and we'll also apply user-defined functions to solve problems and code solutions. And all of these topics will be doing kind of this final big goal as well of reviewing important topics for computer science certification examination and or from curriculum standards.
Thanks so much, Michelle. While we're getting switched over and switching our presenter, I just want to mention this is the second in a 4-part webinar series focusing on advanced topics in computer science. So if you happen to miss our first one, don't panic. I'll automatically show you at the end of the webinar where you can go back and download that first webinar's content and play back. And again, it's something that you can do at your own pace for free. Tony, it's all yours.
Thanks, Mike. And I also wanted to add that the next webinar on advanced topics in computer science will be on manipulating text with string processing. So that one will be coming up on April 30th.
Awesome. Thank you.
All right, Tony, can you see my screen okay?
I can. Thank you.
All right,
So
let's jump
look
in.
at, we can look at the standards. So let's talk about on the certification exam, the 241 exam in Texas, we're going to be looking at some of the standards. The computer science teacher correctly and efficiently uses data types, data structures, and functions in the development of code. And we'll specifically be looking at the beginning teacher demonstrates the ability to create user-defined functions and procedures, and the beginning teacher traces, compares, and uses iterative and recursive algorithms. So we're going to start off looking at recursion. So this is a foldable that Michelle and I created to be able to work through this idea of recursion. And so if we can, Michelle, let's take a closer look at this in more detail. So when Michelle and I first started coding, and Michelle, feel free to jump in here. When we first started coding on the Nspire, we didn't know that we could even tackle a concept like recursion. And it wasn't until we discovered how to use functions with TI Basic that we realized that recursion was possible. So what we want to do is we want to look at this idea of what a function is, and the purpose of a function is to return a value. And we found out that functions can be a lot more versatile than programs. So if we look at this idea of recursion on the foldable, let's look at the overview. So these are my three big ideas about recursion. It's a method that calls itself. And so it's going to call upon itself sometimes over and over again. The other thing, too, is you have to have a base case when you have recursion because it has to have a place to stop. And the third big thing that I see is that it's a memory hog because it's constantly calling upon itself until it reaches that base case. It uses a lot of memory. Do you have anything to add to that, Michelle?
Yeah, one thing I'm wondering, like, can you talk a little bit more about this first idea, like a method that calls itself? Like, we have this example in the bottom left of a recursive function. So, like, what does that mean? Where are you seeing that?
Right. So it's almost like we have this function, and we want to find f of x of this function, but when we try to find that, it's using f of x minus 2 in this example. And so it keeps repeating back to that, and we have to keep solving backwards until we find the answer when we reach the base case. And so let's look at what that looks like, what that example looks like. If we talk about this recursive case that I'm mentioning, it's a situation where another method call is made moving closer and closer to this base case. Because if you notice, under the else statement, return x plus f of x minus 2, that's going to be our recursive case. Notice that there's another function in there. So instead of it solving for x, it's calling upon another function in that statement. But if we reach the base case, which is our second definition here, it's the terminating situation in a recursive program that doesn't use recursion to produce an answer. And that would be up where the if x is less than 1, then return 2. And once we get to that base case, then we're able to go back and solve all the other f of x's and find out what our initial answer was that we were looking for. So let's look at this program in a little more detail, if that's okay.
Yeah, I think that's a great idea, because I remember the first time that we looked at recursion, Tony, we were like, what? Like, that's a lot of vocab, and what does that mean? And then when we saw some worked examples and tried some ourselves, we're like, oh, okay, this is totally possible.
Right. Thanks. So look at this program that we put together, and we wanted to find f of 5. So notice up there that we have a method header, and this is a function instead of a program, and we're going to look at how we can create something like this. But what if I were to put 5 in for x, where the cursor is? So I want to find f of 5. And so I'm going to go down to the if statement, and it says, if x is less than 1, then return 2. In this case, x is not less than 1, so I'm going to go to the else statement. And so it says return x plus f of, in this case, x minus 2. So what happens when I put 5 in there? What am I going to get back? If you can put some ideas maybe in the chat and tell me what you think I'm going to get when I put f of 5 into that statement after the else. So I see, Michelle, I see Jenny said,
yes,
if we put f of 5, when we put 5 in there, we're going to get 5 plus f of 5 minus 2, which is f of 3.
Okay, so I think I just put that on the screen as well, some of the different ideas we're getting to. And it looks like some people are going further down, like actually working the recursion out, but like
right.
we can't really put 5 and f at 3 together, right? Like we can't say, oh, there's a 5, there's a 3, that's 8. Like that f at 3
right, because we don't know the f of 3. So we don't know what f of 3 is. So now we need to solve for f of 3, right?
Got it. Yep.
So let's try that. So if we now have 3 in there, 3 is not less than 1. So we're going to jump down.
So you're running it. Okay, I'm going to jump in for a second. You're actually running the function again and now plugging in 3 because you're trying to find f at 3. I'm with you. Okay, keep going.
Okay. So when we compare 3 to the 1, 3 is not less than 1, so we're not going to return 2. We're going to jump down to the else statement again, and now we need to put 3 in for x here as well. And so what do we end up there?
And that's what Danielle was sharing in the chat as well. And y'all, please feel free to keep sharing your thinking in the chat as we go. Danielle was saying that f at 3 would return 3 plus f at 1.
Yeah, perfect. So, but
okay. Can we put those together?
We don't know what f of 1 is, so we have to keep going. So now we're going to go back up to the function, and we're going to put 1 in for x. And so we go back to the if statement, and is 1 less than 1? No, so we're not going to, yeah. So we're not going to return 2, so now we're going to move down to the else statement again. And so we would have what at that point? And
does anyone want to second does anyone want to second what Danielle has in the chat? Looks like Siobhan thinks the same thing, that they're saying f at 1 would return 1 plus f at negative 1. Does that sound right, Tony?
Yes, that looks great.
Okay.
But we don't have anything that tells us what f of negative 1 is either. So we're going to have to go back. Are we just doing this
all night? Like, do we just, is this the whole webinar? Like, we keep going forever, and at the end, we're just not done, you know?
And I can see where this could be a memory hog, right? Because we're just going and going and going. And so when we go back up and we put negative 1 in for x, now when we get to that if statement, negative 1 is less than 1, so we can do the then part of it, which is return 2. So we should come out with something with f of negative 1, and I think Danielle hit it, and Marcy and Siobhan are giving you answers as well, Rodelio. So f of negative 1 equals 2. So we've hit that thing that we call that base case. We finally got an answer.
And it's the base case because we didn't end up with another function call. Is that right? We finally, like, we didn't have to keep going. We knew a number finally. Is that right?
Yes. Perfect. So now that I know that f of negative 1 is equal to 2, what can I do with that? How will that help me get back to my original question, which was f of 5?
Yeah, like we found out what f at -1 is, but who cares? That wasn't our question. Our question was f at 5, right?
Right.
Sarah has an idea in the chat. Do you see that, Tony?
Yes. So we should plug that back in. Okay, I see what she's saying. So we should take, because up right above our base case here, we have an f of -1. We have 1 plus f of -1, but now that we know that that's equal to 2, we could plug 2 in place of that. Perfect, thank you. And so now we know that f of 1 is 3.
Got it.
Okay, that's helpful. So now if we work our way up again, because now that I know that f of 1 is 3, what can I do with that?
Okay, f at 1 is 3. Got it.
And so I see Rogelio giving us some ideas. So now we know f of 3 is 6. That's going to help us because now we can plug in 6 in place of f of 3.
Got it.
And we get that f of 5 is equal to 11, which is what people are telling us in the chat.
And then Paul adds that Dean
a long time ago.
So true, but now if we think about it, we've created a convincing argument to show why that's the case, right? Like why with confidence we think that this function would execute and return a value of 11. Should we check it, Tony?
Yes. Yes, let's check it on the Nspire and see if that's what we get.
Okay. So this is the function we were just looking at, f at x. And I'm going to, I'll go ahead and go into the menu, check syntax and store, and run this program. And in the future, I'm going to use the shortcut Control-R. And when we run it, what value did you want? F at?
F of 5.
5? Okay, let's see.
Yeah.
11.
That's
nice.
Exactly what we wanted to get. Awesome.
Neat.
So, so Michelle, let's see how we actually write one of these, how we create one. Let's go ahead and create one from scratch, if that's okay.
Yeah, no, that's a good idea. I'm going to add in a new program, or a new problem.
Okay, great. I was going to ask you if we could do that because that would allow us to call this particular function f as well if we wanted to, right?
Yeah, I think so. So we're going to do a new program, so add program editor and new, and then you said we're going to call this function f, just f like that?
Yes. So here's where we're going to change the type from program to function.
And this is interesting because, like you said earlier, Tony, we did a lot of coding on these for a long, long time, just in programs, and we never knew like what functions did or why you would ever change over to a function instead of a program. But recursion is a great example of that. When you want to return a value, not just display a value, but return a value to do something with, functions are your friends for that.
Yeah.
Okay, so now what?
Okay, so now there's a couple of things. First of all, anytime we're doing this with a function, we need to have a formal parameter. So we need to go up to our define f, and we need to put a variable in there. Usually we put x, right?
Yeah, that's good.
So we can do that. And then the other thing that we probably want to add down here is a control structure. And so let's go in to the menu and let's look at menu and then control, and let's put an if then else in there, similar to what we saw in that other program that we just looked at, or the other function we just looked at. So, so we want to do some sort of a comparison like we did before. So what if we say something like, if x is greater than 5,
okay,
and then on the next line, we want to return. So Michelle, where would we find the return in our menu?
That's what I usually have to search for, to be honest with you, but I think it's in transfers. Yeah, there it is.
Yeah, great.
Okay.
So now if we return, let's do our recursive case here, similar to what we saw earlier. Let's return f of x minus 3 plus 2.
Plus 2. Got it. Okay.
Okay. And so we've got this case, but we know that this is just going to keep on calling another function over and over again. So we need a base case. So let's go down underneath the else and let's put in something like return again.
Okay, return.
And let's just say return 1.
Nice, okay.
So, so this time, if x is greater than 5, we're going to keep calling up that function. But if it's anything other than that, we're going to return 1.
Got it. Okay.
Okay. And I see a question, Michelle, about why we chose to do 2.1 for this. Do you want to address that?
Sure. So earlier when we were on page 1.2, like we could have added other pages. So like, for example, I could add another calculator page. But when I go into variable in that, my function f is already defined from before. So I think of like the number in front of the decimal point is kind of like your chapter, and all the pages in that same chapter share the same variables. So by adding in a new problem, move to chapter 2, I can use this same function name f again, but now it means a different function because chapter 2 doesn't talk to chapter 1, if that makes sense.
Yeah, that's a great way to put it. So how about if we take, you want to take a minute and let's look at this, and what if we wanted to do this for f of 16?
Ooh. So you're saying I'm going to run this, not now, but in a minute, with a method call of f at 16, and we're wondering what the output would be. Is that what you're thinking?
Yes. So I'm wondering if people can tell us in the chat, how would this start with f of 16? What would that look like?
Okay. Yeah, so maybe take a minute or two, y'all, and just kind of share your thinking in the chat, however you want to kind of note that. You could also kind of be jotting some of it down on paper. And you might, your goal will be to think about what would f at 16 produce in the end, but you might want to share some of your thinking along the way to convince each other of your answer, right? And Tony, I wonder if we have this in the slides too. I'm going to jump over. I won't show it the whole way through. Oh yeah, is it okay if I show it like this?
Yeah.
That way people can see
Yeah.
the call as well? Okay.
Perfect.
Okay, so take a couple of minutes and share some of your thinking in the chat, and just take this opportunity to kind of work through this recursive example, take some risks, share some of your thinking with the group.
So I see Danielle has some ideas. Let's see if some people agree with what she's thinking for f of 16.
Yeah, if they either agree or if they can add on, like is there a next step type thing. See, and what I'm wondering about 15 is, like, I wonder how we get 15. Like, is f at 13 plus 2 equal to 15 just because there's a 13 and a 2? Do you know what I mean?
Ah.
Because because Jacob's giving another idea, he's got f at 16 equals 9, and Marcus is thinking 9 as well. Do you know what I mean?
Right. Yeah.
But how come,
so let's look, go ahead.
I was going to say, can't you just do the 13 plus 2 equals 15? Like, can anyone share about that in the chat? And then, Tony, do you want to talk through this one?
Yeah, so I was going to say, let's look at that while we're getting these ideas in the chat. Let's look at that first step of f of 16, because 16 is greater than 5. So when we look at our if statement, so we're going to put it in f of 16 minus 3 plus 2. But the 16 minus 3 is inside of that function. So that's going to give us f of 13 plus 2.
That's neat. And Marcy just shared something in the chat that I think is worth sharing with the whole group. She said, oh, it's going to keep going because it's not 13 plus 2, it's f at 13 plus 2, right? And like this f at 13 means something. It means run the function again with an input value of 13.
With 13.
Yes?
Yes.
Maybe?
Thank you for that. So
thanks all for sharing your thinking in the chat. That's really powerful.
Yeah. So here we go again with this function because we don't know what f of 13 is, right? So we've got to go back to our function and now use 13 in place of x.
Got it.
So what would f of 13 be?
Maybe something like this. I've seen this shared in the chat a couple times as well.
Yes. And so we're starting to get, and I think people have been working through it because I'm starting to see an answer over and over again. And as you go through it, and then we end up with f of 10, so now we've got to put 10 in for x. And we end up with f of 7. And then we get f of 4. And at this point, I see a couple of people have said, wait a minute, when we go back and put 4 in for x.
Okay.
What's going to happen?
And that's interesting because sometimes when I'm doing recursion, I just get in the pattern that I'm doing. Do you know what I mean? I'll write f at 4 equals f at 1 plus 2. Do you know what I'm saying? Instead of thinking, no.
Going.
Yeah, oh, I'll recurse all day, no problem. Instead of like pausing and thinking about, no, like you're actually running this through the function and you have to check, is your new value of x greater than 5 in this instance? I love too seeing people share in the chat about calling this the base case, right? Like using that language of recursion.
Right. And so once we got to that 4 that was not greater than 5, we jumped down to our else statement. And so now we're ready to work our way. And somebody said, now we need to go backwards and we need to plug each answer in as we move backwards. And I see you're doing that for us.
Yeah.
So we put our 1 in, and now we know f of 7. Once we know f of 7, we can replace f of 7 with 3, and that helps us to find f of 10 is 5, and now we can replace f of 10 with 5, and that allows us to find f of 13, which is 7, and now we can replace f of 13 with 7, and that gives us f of 16, which a lot of people figured out earlier that was 9.
But this helps me see why f at 16 isn't 15. Do you know what I mean? Because that's tempting with that 13 and that 2 side by side. This helps us really, again, make that convincing argument to show why we think, fingers crossed, that this function will return 9 when we execute it with a method call of f at 16.
Absolutely. So you want to try it, Michelle?
I do. I always get like a little half bit nervous when we're about to do this, like, oh, what if it doesn't work? But we'll try. Okay, so here's our function that we wrote earlier, and we created that one together, and we want to run f at 16. Woohoo! That makes me happy, like every time when those work out. So.
Me too.
Awesome. And y'all, thank you so much for sharing not just like your work in the chat, but also your thinking in the chat, because it really helps us learn from each other and kind of think about like what we know and what we're still learning and ask questions. So that's wonderful.
Absolutely. So Michelle, do we have time to do a little challenge problem and see?
I think we do, and these are fun in a nerdy way. So like, there's 2 choices though. Do you want to do one that has, I guess we can ask the group too, like I guess this would be option A, one that has 3 choices? Or option B would be one that has 2 variables. Eek! Yeah. Quick polls, anyone have a preference if we look at option A, which has 1 variable but 3 choices? Or option B that has 2 variables? And if there's no preference, it'll be Tony's call.
We've got an A and a B. Let's see. Oh, Oh, people want to see what's happening with two variables.
I have no idea where to begin on B. That's good. That's a great place for us to start. So, all right, y'all, I think it's B.
I have no idea where to begin, so let's try this one, you know?
Yeah, so. let's do it. And let me also say that this slides presentation is in the resources that Mike will share at the end of the webinar, and it also comes to you by email. So you'll also have the other recursion challenge that you can work on, and then also, like many of you have a TI-Nspire calculator of your own and or have the software or can get the software, the 90-day trial. So you can actually try these out yourself as well to test and see if like what you think will happen is what will happen. So yeah, how do we even start with this? Like, what are your thoughts, Tony?
Well, the first thing I noticed is it's asking for F of 520. So I'm thinking maybe we should start just like we did before. And so, you know, we're going to go up there to the very top and we're going to put 5 in for X and 20 in for Y. And so we'll start that when we get to that if statement. So that's what I'm thinking we should do. And the if statement is having us compare X and Y. So I'm going to put 5 in for X and I'm going to put 20 in for Y.
Yeah, okay. So 5 in for X, 20 in for Y. So then if 5 is less than 20, is that right?
Yes.
Okay.
Then we're going to return that, and 5 is less than 20, right? So I think that's going to be my first step right there. I'm going to look at F of 5 plus 1. And
okay, 5
and 20 minus 5, and then plus 2 outside of that. That one is complicated.
That is, and I just tried to capture in the chat what I think you were saying out loud. So I think you're saying that F at 5, 20 would return F at 6, because that's X plus 1, 5 plus 1, comma,
right.
15, because that's 20 minus 5, and then yes. Plus a 2 at the end, plus a 2 on the outside.
Yes.
Okay.
So I think that would be our first step. So you want to give everybody a chance to maybe try the next step?
Yeah, that's a great idea.
We need F of 615 to be able to find the answer, but we don't know F of 6, 15. So now we've got to go back to the function, right?
Yeah, go ahead and then plug it in and see what happens. Yeah, so let's give everyone a chance, like you said, and then there's some good chat going on as well about Sarah has what she thinks is a base case and was wondering if someone could kind of check that or confirm that for her. So yeah, take a minute, everyone, and let's kind of work through this. You're welcome to kind of share your work as you go because that might help others kind of track their thinking too.
So we're getting some ideas about the base case. So I think, Michelle, everybody's pretty anxious to find out if the base case is 10. Because I figure once we know that, we can start working our way backwards, right, to solve F of 520. Right.
So I think it just looks like we're maybe missing some intermediate steps. So, like, we know we needed F at 615, and so I guess that would yield F at 7, 9 plus 2. And then we would need to know what F7, 9 is?
9, yes.
Which would be
F of 8,
comma 2. And you're getting that 2 because you're doing the Y minus the X, okay. And then plus the 2 at the end. And then, and then F at 8, 2, we finally failed that if, right?
Okay, right, because if X is 8, and Y is 2, then X is not less than Y. So I'm going to jump down to the else, and it says to add the X and Y together.
Right, right, and some people are noting that in the chat too.
Yeah, so now I see that they got f of 8, 2 is equal to 10, and that's our base case. We now know what 8, 2 is.
Yeah, so there's a good question, there's a good question. So when I run f at 5, 20, does it return 10? Because that's the base case?
No, that's not going to happen because f of 5, 20 is not going to be the same as f of 8, 2. So we know f of 8, 2 is 10, but now we're able to work ourselves backwards up through. So if we can find that statement where we use f of 8, 2, and I think that was f of 7, 9. I'm looking at your statement in the chat. F of 7, 9 is equal to f of 8, 2. I'm going to substitute 10 there. And so I get that f of 7, 9 is 12.
Yep.
So
and
now
I'm thinking in the chat, about plugging them back in all the way up until you get to f at 520, right?
Yes.
And this is a great illustration too of why we actually animated some of these slides back here like we did, because there's a lot to keep track of, right, when you're doing recursion. And so you'd want to kind of keep track of all your previous equations that now you could go back and substitute in.
Yeah. And so I'm seeing a lot of people are thinking that the answer to f of 5, 20 ends up being 16. So do we have time to try it and see if that works?
I say we just leave them hanging, you know, and I'm just kidding. I'm just kidding. Let's try it and see. So I think this is the same function. So I'm doing a quick check. So it looks like the one we were doing. And let's try it. Control R to run it, and it was 5, 20, maybe?
Yes.
Okay. 16. Nice, y'all.
Awesome.
Nice.
Very nice.
And what's interesting here is, like, all of our intermediate work is done behind the scenes in the calculator, right? Like you're saying, it's a memory hog. Each of those function rules is open until it gets the info it needs from the base case, and then it closes all the functions as it works back up to answer the real question. So all we see is this final answer, but this is really helpful for checking recursion problems that you're working by hand, like this one, and then you just want to check and see if your thinking kind of matches with what would actually be output by it.
Yes.
That's key.
That's awesome.
All right. So again, there's another recursion challenge in the slides. You can take a look at that. There are other examples in some of the materials that y'all are using to prepare, or many of you are using to prepare for a certification exam. But FYI, you can enter recursive functions in your Nspire and then use them to check your thinking.
Great. So Michelle, do you want to talk a little bit about user-defined functions?
Yeah, I think that's a good, I think this is a good transition point. Let's spend maybe 15 to 20 minutes looking at some other examples of user-defined functions that kind of go a different way. So let's start by looking at, so we're totally switching gears here. A minute ago we were looking at recursion, now we're looking at some other programs that we might write. And we're going to look at this program, which is called predict. And I'd like you to notice that the method header, kind of this part up here of the program, contains two formal parameters. So remember that our formal parameters are kind of our placeholders, if you will. We will pass actual numbers into this program, but these act as placeholders here in our program. So when we run this program, this means that the program will require two actual parameters, two values, in order to be entered into the method call in order for this program to run. So let's take a look at what's kind of going on in this program. First thing that happens in this program is we actually define another program. So we have a sub-program here called prod. And underneath prod, so this section is where we've defined this other program called prod. And underneath that, we actually return to the main body of the program. So this down here is actually the main body of our predict program. This is just another function that another program we're defining within it. So we'll analyze this code in detail in a few minutes. But first, let's each kind of map through this program and predict what we think will be executed if we run this program. Say we run this program with a method call of predict 3, 5. 3, 5. So I'm going to go back into the program and imagine I run this program with a method call of 3, 5. What do you think is going to happen? So take a minute, kind of trace through the program on your own, and share some of your thinking in the chat. And thank you, Tony, for sharing in the chat the method call that we'll use, predict 3, 5. And again, like, be vulnerable, take chances, share some of your thinking, even if it's with question marks, like I'm not sure, or I'm not sure what this part will do, but I think this will happen later in the program. Share some of your thinking about what you think will be displayed when we run this program with a method call of predict 3, 5. Okay, Sarah has a great question. The X and Y that are within this kind of program definition are called your formal parameters. And so they just act as placeholders kind of on the back end of the program. But then when we actually call and run the program, we have to put in real values for them, and those are called your actual parameters. So this 3 and this 5 represent the actual values we're going to pass into the program. And the X and Y represent kind of the placeholders that are used internally. Great question. We'll talk about the A and the B in a second, Sarah. Good question. So seeing some predictions, and again, feel free to share your thinking, also explain like why you think that, and no problem if we're not sure, like let's take chances and share some of our conjectures. So we're seeing some lots of great predictions shared in the chat. And so to test these out, so some of the predictions are things like there'll be a 15 and a 3, 5 and a 15 and a 3, 5. Maybe there'll be a 15 and a 15. And then another response is, I think it'll show a 15 because we're plugging 3 in for A and 5 in for B. So let's see what happens. I'm actually going to, let's go run this, and then we'll test this against our predictions and see what we think. So I'm going to come over here, and we're running predict 3, 5, and we get this, a 3 and a 5, a 15, and a 3 and a 5. So I'm going to go back to the program, and I'm wondering if we can like make sense of this now. When we ran this program with actual parameters of 3 and 5, we saw a 3 and a 5, 15, and a 3 and a 5. So let's kind of decode this line by line. It seems like this should happen first, right? Like that this product should happen. This is like the first thing that happens in the program. But note that here we are just defining this program. We are just saying, hey, we're going to make up a little subprogram called product. It's going to take in 2 values, and then here's what it's going to do with them. But we're not actually calling this program, like we're not actually telling this program, hey, run right now. We're just saying, hey, here's the info. Here's what you will do if ever this program is called. This program actually gets called for the first time down here. This is the first time that that program actually gets called. So this section is just a definition. So we can read through it as we're working through, but nothing actually happens when the program runs, like nothing displays just because the program reads over this part. Our first actual output will be right here, disp X and Y. And X and Y in our case were, I've already forgotten, 3 and 5. So we'll display 3 and 5, yeah. Then after doing that, it's going to go to the next line. It's going to say, oh, you're going to run this program called prod, and be like, what? What is prod? Oh, wait, let's go check our notes. Here's how we've defined it. When it tells us to do prod, we're going to do this. But what are we doing product to? Like, we're doing product of X and Y, so that would actually be the prod of 3, 5. Is that right? So that 3 and that 5 would get passed in here, and it will display the product of those 2. maybe. So again, you can share some of your thinking or questions in chat. And then after displaying that product, it'll display the X and Y values again.
So Michelle, I see a good question here from Nikki that says, do you have to put any of the defined programs before you display anything, or could you display the first X and Y before you ever define the other program?
Oh, good question. So let's try it out. So could we disp X, Y up here? What do y'all think? Do you think, will that work to say disp those and then Y? And then what if I also do a prod of X, Y up here? Do you know what I mean?
Oh.
Like, are those, will either of those, will both of those work? So we'll try one of them first. I'll get rid of this one. And we'll just try the display first. Let me run it.
Okay.
Oops. Oh, silly me. What did I do on there?
We need our 3-5. We need our, we forgot to put our actual arguments in.
Yeah, so remember when Sarah asked earlier about like these are our formal parameters. This is telling the program, hey, you need to have 2 values coming in. And then when I ran it, I forgot to put 2 numbers in, so I have to tell it 3-5. So sorry about that. That was my error, not the program's error. And that one worked. It did our first disp, then did our later disp, and our prod, and our other disp, okay? But then Nikki's other question might have been, okay, but instead of just the disp, what if we tried to call prod up here? And I'm curious, oh, should it be AB? Maybe it should be like XY. I'm not sure if this is gonna work. Let's run it. Oh, I did it again. That's still my same error. Sorry, right?
We all do that one. We get used to
oh
that
my gosh.
error.
Yes. Okay, let's actually try this again, passing in the 2 actual parameters. Now, it worked, but y'all, it shouldn't have, and let's talk about why it actually worked here. The reason it worked is because we had actually already run this program once, and it had already defined this program called prod. Do you know what I'm saying?
Yes.
So if I change this to a new title, like prod 1, do you know what I mean?
Mm-hmm.
So now this is a new program. We're going to call this program prod 1. It has never been run before. And now if I call this program before it's defined, I think this is going to give me an error. Let's run it and see. And I'm going to put in my 3-5 this time. Look at me learning. Ooh, look at this error, y'all. Function is not defined. And let's go to see where the error is occurring. And takes us right to this point.
We were calling on that prod 1 before it was ever defined in the program.
Exactly right. And so, Nikki, back to Nikki's question, if you are going to create your own functions or your own programs within a program, you have to define them before you call them within the program. And so that's why a lot of times when we're looking at programs like this, we'll have some of these kind of definitional things up front. And we just kind of read through them, and I kind of think of them as like a dictionary, like, oh, so note to self, if ever this program comes up, here's where I refer back to find out what it does. But we're not actually doing this program until it's actually called down in the body of the program itself. Thoughts on that? Great questions, y'all, and good thinking kind of shared within the chat. Okay, so I'm trying to think of where to go next with this. I'm going to actually redefine this back to prod. It doesn't matter. I mean, the name really doesn't matter here. But here's what I'd like us to think about this time. We're going to make a couple changes to this program and then predict what the output will look like. So what if I add in a line where I call prod again, but this time I'm going to call prod of 0, 0. So take a minute and I'd like you to kind of share in the chat, what do you think this program will output this time if I again call predict at 3, 5? What will the output look like this time? And while y'all are kind of thinking about that and sharing about that, I'll answer Sarah's question. She had a question of, Why is the program stuff necessary? Can't you run the prod function without it? Great question. So there are lots of functions we can run without the program part. Things like Sarah, there's a function called int for kind of like the greatest integer less than a number. That's a function that's built into the Nspire. What we're doing here is we're creating our own brand new program called prod. It doesn't exist in Nspire. We just kind of made it up and made it do this thing. So this is an example of what we call a user-defined function where we create our own program or function or subprogram, and that's why we need this kind of defined part or whatnot, so that our program knows what to do when it encounters that made-up program we had. Okay, so I'm seeing a couple predictions come in. People are saying maybe it will display 3, 5, then maybe it'll display 15, then maybe it'll display 0, and then maybe 3, 5. Let's run it and see what happens. So we're going to run it with actual parameters of 3, 5, and test and see what happens. 3, 5, 15, 0, 3, 5. Oh, so this is interesting because there's some thinking in the chat about, like, why did prod at 0, 0 return 0? Like, that wasn't, some people are saying, was that defined? So does anyone have any thinking about that? Like, has this been defined? Why did this run? And here's what I'll have us think about. What we defined up above is the program called prod. And as Shelly's sharing in the chat, you give it values. So we could run prod at XY. We can run prod at 1, 2. We can run prod at any different values. We have defined this function called prod, and it has to get 2 values coming into it. And those values could be numerical, like we're showing here, or they could be numeric variables, like the x and the y, that are coming in from earlier in the program. But prod should work for any 2 variables we pass into it. So let's run this and kind of see.
So Michelle, once you define prod, then you can call prod for any values you want inside of that program, right?
That's exactly right, and that's one example of why you would ever do this. Like, why would you ever create your own functions? Because there might be something you want to do again and again and again, but with different values each time. And so here we're using values of x and y. Here we were kind of giving it these values arbitrarily, like, but we could also do something like, I think we've got time to do this. Y'all, I'm going to add in one more challenge, and then we'll show you kind of an example of this as well. Okay, y'all, now we're getting crazy. We're in the last few minutes. What if we did something like, okay, so back to our original program here. Display x and y, prod at x and y. Then we're going to do this, x gets x plus 3. Can someone share in the chat what this line of code will do? X gets x plus 3. So I've added in 2 lines of code. I've added in x gets x plus 3, and then I've added in another prod statement where we're going to display the product of x and y. So if you will, take a minute and predict in the chat what's going to be output this time when I run predict at 3, 5. And if it helps your thinking, Jenny is sharing that the x gets x plus 3 adds 3 to your x variable and then stores that value back into x. Nikki's saying it replaces the current x value with the number increased by 3. Sarah kind of seconds or thirds that. Whatever x is, it adds 3, and then it will be your new value. So now my question is, what is going to be output when this program is run? What do you think we'll see when we run this in just a second?
Because when we change that x value from our initial x value, that's going to change our prod when it goes up and runs it, right?
Ooh, so you're saying that this prod, the second prod, is actually going to have a different output than this first prod? even though they look exactly the same.
Yeah, that's what I'm thinking.
Okay, and I'm seeing some people kind of second that in the chat. Some people are saying, I'm expecting a 3 and a 5, then a 15, then a 30, then a 6 and the 5. Let's see. Ooh. Again, I always get nervous at this part. So 3, 5, let's see what happens. Ooh, check that against what we were thinking, against our conjectures. Display X and Y, then their product. But how come this product was 30? Because of what Nikki and Sarah and Danielle shared earlier, and Jenny shared earlier about our X value went up by 3, right? So this was the product of 3 and 5, but this was the product of 6 and 5, right? Is that right? Neat. Awesome. Thanks for sharing your thinking in the chat, everyone. So there are a couple more examples of these kind of define your own function challenges in the slides presentation as well. And again, think about Sarah's question earlier, why would we do this? When we want to create our own function, and it could do something like multiply 2 numbers, it could multiply them and add something on as well, or add on a square. I mean, you can make that be whatever you'd like it to be, and then when it gets called, it will come up here and do whatever this program says. We're in our last few minutes, so I wanted to show y'all an example from Rover. And so the Rover is a programmable robot that works with your calculator, and this is an example of a user-defined function that's for Rover. So in this particular function, we're going to do a for loop to do these sequence of commands 4 times, send the Rover forward, wait a second, then we're going to call a program called color. And over here, you see the program for color. And what color is doing is randomly picking an R value between 0 and 255, a G value between 0 and 255, and a B value between 0 and 255. And it sends those values back into the program, which then lights up an LED with this random color. Then the robot will turn left and move through the loop again. Tony, what are you thinking?
So I'm thinking, so those random numbers that it's sending are going to send different colors, mixing the red, green, and blue with whatever random numbers it comes up with?
Yes, we think so. So let's actually watch this program in action. So notice lights up a color, moves, lights up a different color, moves, lights up a different color, moves, lights up a different color. So you can actually see it calling that random color subprogram every time that color changes. And so that's an example of when you would write a program, a subprogram, and then to do a specific action, and we included it as a separate program instead of within the whole program so that it made the code a little bit more readable. There's more for you to kind of check out in the slides from today, but we're going to pass it back to Mike to kind of wrap us up for the evening. And as we're doing that, if you'll share a little bit in the chat about something you learned tonight, either about recursion or user-defined functions.
Thanks so much, Michelle and Tony, for everything you shared so far. I do want to mention just a couple last-minute things as we're wrapping up. One's available on our website, education.ti.com. And if you move under the Professional Development tab and check out webinars in the sort of middle column at the bottom, you do a couple things. You could look at some of the live upcoming webinars that we have, one of which I think Tony mentioned earlier is part 3 in this webinar series coming up late April, so April 30th. If you're not already registered, you can register for that. Or you can go to the on-demand webinar series, and you can either just look near the top, it says Advanced Topics in Computer Science, or you could specifically choose, say, coding or computer science under the topics. And there's our part 1 that we used last week. Again, feel free to download this. It's free. You can, again, watch at your own pace. Also on our website, under Activities, that middle column, the first choice is TI codes. If you're not familiar with TI codes, It's a great way to bring your students into the world of coding or yourself. I've personally been using TI codes to learn more about coding because I don't have a coding background. So they're really very self-guided, self-paced, and offer a lot of information. So if you haven't checked them out yet, please feel free to do so. Again, it's all free as well, available on the TI-Nspire platform or the TI-84+E platforms. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents that Michelle and Tony used tonight. And if you happen to miss these links or if they're not working for you for any reason, just hang tight. You'll automatically get a follow-up email in a couple of days. In that follow-up email will be a link to the recording and a link to the documents as well as a link to the certificate. And if you're watching this on demand, just go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Michelle and Tony, for everything you shared tonight. I really appreciate it.
Thanks, Mike.
Thank you.
Thanks again, everyone. We hope to see you back online real soon. Have a great night.